Hi, this is a new video part of the research project Analog Spiking Neuron Model for Unsupervised STDP-based learning in neuromorphic circuits for my master thesis. So as I said in previous video, I wanted in this video to focus and to talk only about STDP. So what is STDP? And I will present in the future video, in the second video, how to train a network using STDP function and STDP learning. So Henry Markram in 1997 he suggested in his paper, after recording pyramidal neurons from rats, that the action potential propagating into the dendrites served to modify single active synaptic connections. And this would depend on the pattern of electrical activity in the pre- and post-synaptic neurons, according to his words. So B and Poo here in 1998, enhanced the proposition, and by recording rat hippocampal neurons, they demonstrated that the relative timing between presynaptic and postsynaptic spiking determines the direction and the extent of the synaptic changes. So repetitive postsynaptic spiking within a short time window, around 20 milliseconds, after a presynaptic activation leads to a long-term potentiation, LTP, right here. And a postsynaptic spiking within a short window before repetitive presynaptic activation leads to a long-term depreciation, LTD, right here. And this is illustrated by the well-known double exponential learning function right here with the LTP here and the LTD here. So, what is well known? What is well known with in the paper from the paper of B and Poo in 1998 is that significant LTP occurred only at synapses with relative low initial strength, whereas the extent of LTD did not show any obvious dependence on the initial synaptic strength, according to the research. So yes, this is pretty interesting for what we will see in a few slides. So Caporal in 2008 presented in his review the fact that there are several STDP functions within different learning windows, and it can vary across excitatory and inhibitory synapses connectivity. And hence, when we're saying that we are using STDP function in our algorithm, it's not obvious, and it's not really clear which one we are employing, because there's different STDP functions, and not only ones. In fact, this one. So this is the one, the first observed, and the one with the double exponential curve. Is the most well known, and at least this is the one I've the most encountered in different papers, and also the first observed in living being. So maybe that's why sometimes in papers when we don't explain which STDP we are using, this is most of the time this is this one. Sorry. So we can see different interesting shape of STDP, like this one where there's only LTD and no LTP, meaning that the synaptic strength can only decrease. And this one is also very interesting, and I used it in a previous algorithm, in an algorithm I will present you, I don't know when. So it's very interesting, and it looks like Mexican hat function. And what is interesting, it shows an LTP, so an increase of the synaptic rate for close timing spiking without regarding if it's positive here or negative correlation. So it means that it can be good for synchronization of signals, and we can compute some stuff with that. So yes, this one is interesting. And also the other one, but I like this one in particularly. So, okay, let's focus on this double exponential right here. The double exponential STDP function. So why is this STDP, and why is STDP great? So as we've seen, first, it's biocompatible. So because it has been observed in living being, and plus it's pretty easy to understand and to implement into spiking neural networks. So as I explained, if a presynaptic neuron, for instance, I3 right here, so if a presynaptic neuron spikes slightly before a postsynaptic neuron, so O1 here, then the synaptic rate will be modified and will be increased here, related to the STDP function Whereas if presynaptic neurons fires slightly after the postsynaptic neurons, right here between this one and this one, the weight omega-2 here, the weight will be slightly decreased related to the considering the STDP function. Sorry. So also STDP is often called causal Hebbian rule. Why? Because first it agrees with the Hebbian rule, saying that neurons which fire together wire together, and this is pretty well known rule in neurosciences, and it goes further by adding a causal rule with postsynaptics firing before or after the onset will impact the synaptic change, and so the wiring. So the STDP function is depicted by those two equations. It's two exponential curves with which tends to zero when the relative timing between spikes tends to minus, or positive or negative infinity. So delta t here tends to positive or negative infinity. And then the implementation is very simple, and it's just that the new weight, the updated weight, is equal to the previous weight plus a variation of weight conducted by the STDP multiplied by a learning rate, which is often used in machine learning. So the STDP function can also be implemented in neuromorphic circuits, as it was the subject of my research. So I've already introduced neuromorphic circuits and neuromorphic systems in a previous video. I will provide you the link in the description, and it's a field gaining considerable attention thanks to multiple advantages, like decreasing significantly it's decreasing significantly the energy consumption. And here is analog circuits of a synapse replicating STDP equations for its intrinsic behavior, and plus it adds an intrinsic excitatory postsynaptic currents generator in order to propagate the action potential to the through the postsynaptic neurons. So here you may not recognize at first sight the STDP evolution that we've seen just before, but it's because it uses tracer methods of implementation, and I won't talk about this method of implementation of the STDP in this video. It's not really the subject, and there's already very good and clear explanation on Brian 2 tutorial, so you can just Google Brian 2 and STDP, and you will see that it's very simple to understand. And so this was just a quick slide, to say that fully analog networks, spiking neural networks, exist, and it's possible to create a network with analog neurons and analog synapses conducted by STDP, and so they are consuming a very, very ultra low energy. So it's pretty good, but still not really efficient, and a lot of research are currently conducted in this field. So the learning STDP is a local learning rule. Only neurons directly connected together can affect the synaptic strength, and it could make sense because neurons which are separated by several layers would have, at first sight, no reasons to affect the strength, the synaptic strength at least, like it is the case into backpropagation. And plus, as we've seen, it's also causal, and it follows the Hebbian rule. So maybe that's why it's a learning rule pretty easy to accept and to understand. So it's very cool. It makes sense. It's a law which makes sense. It's also biocompatible. It's also pretty easy to understand and to implement. But of course there's a but. And first, it's a local and unsupervised learning. So I've already presented what is unsupervised learning. I've already done a video about the subject, and we've seen that unsupervised learning is limited to only a certain type of application, like clustering. So STDP on its own. It's limited to certain type of application, of learning application, and also it's not really efficient. It's not really efficient on its own. It barely gives a good accuracy on simple problems such as the list data sets. So in fact, it's because, for instance, nothing in the function enables to limit the weight. So the weight can vanish or they can exploit without any bounds. And so a clipping function is often added into the algorithm in order to just limit the weight evolution between a minimal and a maximal values. So it's not a really elegant method, but still it works, and the function needs to be limited. Plus, more training do not necessarily guarantee a better accuracy. So there is no gradient descent enabling to tend to a local minimum, or there's not even any apparent loss function. So that's why there's numerous of variations of STDP. For instance, adding surrogate backpropagation, or we can add some rules like neurotical or like modulated STDP and so on to enhance the capabilities of the STDP. So it often needs to be combined. And right here, I'm not going to present all of those algorithms. And by the way, it's absolutely not an exhaustive list. It's just few learning algorithms from papers I've read recently. So you may notice here that STDP can be employed as much for supervised learning with, for instance, STDP, SSTDP, also for reinforcement learning with modulated STDP, or for basic unsupervised learning with STDP or with triple STDP and so on. So in fact, STDP is just a learning rule which is often and which can be combined and coupled with other learning techniques. And yes, that is what I wanted to say in this slide. So there are a lot of training algorithms for spiking neural networks, and STDP is not reserved to only one type of learnings. It needs to be combined. So if you want to remember something, you can remember that there are several different STDP functions, and it's a very interesting and a well-known learning function, but it does not work miracles, and it often needs to be combined with other functions for effective training. So I will publish another video about the modeling of analog neurons and also the unsupervised training with STDP soon. And so it was a pretty short video. I hope you enjoyed the video and you've learned some stuff. And yes, that's all for today.